Hi, my name is Janitha, UOW ID 19537894 and IIT ID 20220212. So this will be my project demonstration for GameAI Coursework 1. The project is split into two sections, section 1 and section 2. The section 1 contains the AI and the NPC behavior, while the section 2 contains procedural terrain generation and the final implementation of both of the sections combined together. Go to section 1 scene, as I have loaded in the screen right now. If I go ahead and play, I will quickly show you how the enemy moves through the terrain, and I will again explain how the enemy states changes throughout the time. So I have created this level using cellular automata algorithm. So rather than a simple placement, by iterating through two prefabs, which is the wall prefab and floor prefab, so this creates this environment that AI can take cover and flee, and where I can move around freely throughout the map, throughout the level. So, and also as you can see, there are squares which is a bit darker in the floor. So this is a weighted terrain system. So each time enemy tries to go through one of these cubes, it creates a penalty. We can imagine that as kind of a mud system in a terrain. As you can see, the enemy tries to avoid the muddy terrain as much as possible. So there are two types of enemies in this level. Enemy which uses A-star algorithm and another enemy which uses normal unity nav mesh. The nav mesh agent is driven by advanced finite state machine, which uses 4 stages, which is attack, chase, patrol, and take cover. Now let's try to closely observe the enemy's behavior when the player is around it, and when it attacks and when it flees. So go to the scene. The default behavior of the enemies is in a patrol state as default, and if I go ahead and go near the enemy, as you can see, the state has been changed into chase state, and when the enemy is near me, it changes into attack state. So these values can be changed, attack range, chase range, and all of the other variables. So these red eye enemies are the enemies that uses nav mesh. If we go to the A-star algorithm enemy and take a deeper look, as you can see in the debug scene, you can see how the AI calculates the path when it chases the player around. So if I get this side by side, you can see the A-star algorithm calculates the distance, even though if I am behind corners and if I go out of the range, it recalculates its path using the A-star algorithm and follows me around. So we can look at another scenario. We'll try to create an area that the enemies cannot move, and we can move the player to that section and try to observe how their enemy behavior changes. And in this instant, as you can see, even though the player is within reach, the enemy state is in patrol because it's unable to navigate through my section using the navigation system. So to make the enemy more realistic, I have implemented flee system, where enemy tries to run from the player when the health gets below 40. So as you can see, the red enemy value is at 100% right at the moment, and if I try to shoot the enemy to get the health below 40%, as you can see, the enemy tries to flee from the player and try to take cover. And when the enemy is too far away from him, the state changes into patrol. So this is the main loop which handles the changing of the states of the enemy, and I have defined each and every state of the FSM. And finally, the enemy takes damage, and I have implemented a UI which shows the enemy state and health of the enemy. So unlike the nav mesh enemy, the A-star enemy agent calculates its path using a custom grid system. There's a function which gets a grid system when the map is generated, and I use that for the A-star enemy algorithm to calculate the distance between the player and to create path to the player using the calculation. So the grid system is specifically designed for the A-star algorithm. It creates a grid based on the map generated after the map is generated, and this is the grid that is used to actually determine the points in the world which are walkable or unwalkable. And finally, when the health drops to a 0, I have implemented the logic where the player can't move. So now we will be moving on to section 2, which is the terrain implementation. Now I have loaded up the second scene of the project, which is the procedural terrain generation. First, we'll go ahead and run the scene and see how the terrain generates. So for this terrain generation, I have used two empty objects, which is object called Smart Spawner and the terrain generator itself, which handles all of the procedural generation parts using Perl invoice. So rather than using a single layer, I have included multiple stacks of layers, which I have defined as octaves. As you can see in the getHeight function, I loop through these octaves, adjusting the frequency, amplitude, and two other variables. This allows me to create like rocky mountain ranges and flat rocky surfaces and many other more combinations using this PCG system. And for the generation pipeline, one of the main challenges was to actually figure out the order of execution. Initially, I was having trouble breaking the nav mesh that hasn't physically appeared on the physics engine yet. I solved this by wrapping an entire generation process inside this generation pipeline. I use this yield return null to actually wait after the generation in the mesh collider. So this enables the physics engine update before I call this nav surface build mesh function. So that ensured a valid navigation graph for the AI every time I spawned in the terrain. By changing these variables, we can go from flat smooth terrains to actually rough, more detailed, bigger height limits and more area to move on. So looking at the spawner logic of this code, I have implemented 6 different types of objects to be spawned, and these spawns will be based on 2 different levels, which is the land level and the water level. So I use these 2 levels to actually spawn different items. And also another thing that it checks is if the player can actually reach the points in the map, and spawning items based on the reachability of the player. So to get the locations of terrain, I have again used the grid system to spawn the items. So we can assign different elements to these different types of objects depending on the location, either above water or on the water level. This will be spawning objects. For this system, it scans the terrain using physics raycast to find extract ground level. So based on different heights, it generates items. So as you can see in this example, a bit exaggerated mountains, you can see all objects are being spawned on the water level, but since the player cannot reach the top level, it doesn't generate any objects. And finally, I will be showing how I implemented a clustering system for the enemies. So unfortunately, the previous project also failed to generate enemies using the k-means clustering. But fortunately, I was able to take some screenshots in earlier build, which it started spawning the enemies using k-means clustering. So I will quickly run through the logic that I have implemented. So this is the main cluster function that I've used. First, as discussed in the lectures, I've defined the centroid enemy, and I have calculated the distance to the centroid enemy. Using that, the enemy circle around a group to show that they are standing together. As you can see in the k-means class, the algorithm iterates 2 data points to assign an enemy to its nearest centroid. Then it recalculates the distance based on the mean. So as in the screenshot, the results are seen as simulation, which enemies form natural groups and squads to create kind of a more coordinated combat experience. So that's my version for the advanced implementation part. So in conclusion of this project, it demonstrated the GameAI principle and combined with algorithms that I've learned in the tutorials. So there are 2 distinct AI agent architectures: custom A-star Pathfinder, which handles weighted terrain cost, and an mesh agent driven by finite state machine. For the procedural environments, it uses both cellular automata generation in part 1 and fractal Perl noise for outdoor generation. So including a level-based spawner with an mesh validation in the procedural generation when it comes to generating objects, and for the final implementation, k-means clustering to create kind of coordinated enemy squads. Thank you very much.